Okay. Oceanic transform faults, as described in the textbook as conservative strike-slip play boundaries. They were first discovered in the 60s. 6 decades passed. We still don't have a very clear understanding why across the globe the transform fault topography varies from a ridge to a valley to a deep valley. Today, I would like to present to you our exciting new findings that may have some interesting implication of plate tectonics. Here's a map highlights divergent mid-ocean ridges in green, segmented by transform faults in red. The total length of oceanic transform faults is about 48,000 kilometers, even longer than the equatorial circumference of the Earth. Grabmeyer 2021 find that as the spreading rates of the mid-ocean ridges increase, the corresponding oceanic transform faults become shallower and shallower. For example, at fast-spreading East Pacific rise, they form the shallowest topography, sometimes even a ridge that's higher than the surrounding seafloor. At intermediate spreading transform faults usually form a small valley less than 1 kilometer in relief. At slow spreading transform faults, usually you see much deeper valley that's deeper than 1 kilometer in relief. Notice that in contrast to fast intermediate spreading rates transform faults, the slow spreading transform faults has a valley for the fracture zone as well. So this is our first question: why transform fault becomes shallower with faster spreading rate? Another global systematic arises when you compare the depth of transform fault and its adjacent fracture zone. Turns out when you plotted the fracture zone against transform fault depth, the one-to-one relationship will plot as this dashed line. As you can see, Grabmeyer find that the fracture zone are consistent shallower than the adjacent transform fault by an average of 700 meters, despite the spreading rates. So this is our second question. To address that, we built a 3D model using the code LAMAM. It simulates elastoviscoplastic rheology, and on two-side boundary, we stretch with a half spreading rate, Vx. And we also implement mid-ocean ridge spreading with dike widening. These two segments are offset, in between which a transform fault arises spontaneously due to plastic deformation. A key model parameter, M, which was introduced by Roger 18 years ago, for simulating faulting and diking along a ridge segment. Now, we extend beyond a ridge segment and intrude a dike into the transform domain and controlled by this MT value, which is the percentage of magmatic extension over the plate separation. And when MT is 1, that means all the plate separation is accommodated by dike accretion within the transform domain. When MT is 0, it has to be accommodated fully by tectonic extension. This design is inspired by bathymetric evidence of magmatism between transform and fracture zone. For example, there's J-shaped ridges across many transform faults between these two places. Also by fresh lava flows observed from deep tow camera. It is also inspired by global systematic of spreading rate dependent gravity. So you see here the residual mantle bouquet anomaly of the transform fault decrease when the spreading rate increase. For example, at fast spreading East Pacific rise, you see low RMBA indicating thicker crust. Whereas at slow spreading ridges, you see high RMBA indicating thicker crust, which is also confirmed by seismic studies. because crustal thickness is a proxy for magma supply, and we have this trend. This allows us to link magma supply within the transform fault MT with the spreading rate, and we're going to focus on this MT. When MT is less than 1.96, which involves about 4% of tectonic extension along the transform fault, we see a deep valley. And notice that the fracture zone now is also a valley, where MT is about 1, which means there's no tectonic extension. Surprisingly, we still get a shallow valley about a few hundred meters deep. When we further increase the MT value, now we get a ridge. Here's a plot of a cross-transform profile, ranging from a topography high to a small valley to a deep valley. Now let's plot the observation for comparison. As you can see, our model reproduces the first order features of the topography, ranging from fast to slow. So as you remember this global systematic, our model, because MT scales with spreading rates, our model reproduced that same trend. So for the first question, here's our answer. Spreading rate dependent magmatism within the transform domain control the global systematics of broad scale transform topography. Let's take a look at a long transform fault topography. As you can see, despite the MT value, the fracture zones are always shallower than their adjacent transform faults. And in terms of the systematics, without even trying, surprisingly, our model reproduced that trend. So why is that? Why is the depth difference? Well, let's take a thought experiment. When the fault is perfectly weak, let's assume we're able to put a rubber band across a transform fault and pin at 2 points, A0, B0. Now let's let the plate move on each direction. Because the fault is so weak, the rubber band will be cut into half, and because there's no shear resistance, the rubber band remains the same length without accumulating tensional strain. Hence, there's no tension across the transform fault. What about when the transform fault is perfectly strong? It's like pinning the rubber band at the transform fault. Now let's as the plate move apart, the rubber band will be stretched and elongated, causing tensional strain and stress, pulling the already weaker transform fault apart, forming deepening of a valley. So this shear-induced tension across the transform fault is only arise across a actively shearing transform fault, but not across the fracture zone, indicating here as the principal tensional stress from the arrows, which is the main reason why we get consistent shallower fracture zone than their adjacent transform fault valley for all models. With that, I will leave you with my summary.